Section 9.7, Probability of Multiple Events. Independent event is when the outcome of one event does not affect the outcome of a second event. The two events are independent events. That is, each event occurs without changing the probability of the other event. But a dependent event is when the outcome of one event affects the outcome of the second event. The two events are dependent events. If one event occurs, it changes the probability of the other event. Mutually exclusive events is when two events cannot happen at the same time. The events are mutually exclusive events. Probability of A and B. If A and B are independent events, then the probability A and B equals the probability of A times the probability of B. Here's a quick example. If the probability of A is 2/3 and the probability of B is 1/5, and they are independent events, then the probability of A and B equals 2/3 times 1/5, or 2/15. If the probability of A and B are dependent events, then the probability of A and B is equal to the probability of A times the probability of B, given that A has already occurred. So therefore, I have to find out the probability of this event after A has occurred. We'll see some examples of that in a minute. Our first example, Jason and Carl each own 4 pair of peanuts. 1 blue, 1 red, 1 white, and gray. Find the probability that both will wear gray jeans today. We're looking for probability of A and B since these are independent events. It doesn't matter which pair Jason or Carl wear because it doesn't affect the other. Therefore, we know they're independent. So we need to find the probability of Jason wearing gray and Carl wearing gray. And the way we do this is the probability of Jason wearing gray, I'll abbreviate that as JG, is 4 pairs, blue, red, white, and gray. There's a total of 4 pair, and only 1 pair that are gray. So the probability of wearing gray is 1/4. The probability of Carl wearing gray, CG, is the same, 1/4. So the probability of Jason wearing gray and Carl wearing gray is equal to each of these probabilities multiplied together. 1/4 times 1/4, which equals 1/16. This is the representation of the problem as a tree. Here I have Jason and Carl. If Jason would wear black, then Carl could either wear black, red, white, or gray. Here, Jason would wear red, then Carl could wear black, red, white, or gray. And again here, Jason would wear white, and then Carl could wear black, red, white, or gray. And finally, Jason could wear gray, and then Carl could wear black, red, white, or gray. And then we have the essence of both wear black, one wear black and red, black, white, black, gray, and so forth, until we really want is this. They both wear gray. And here we have 16 outcomes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And we know our probability of this outcome is already 1/16, as we already found on the previous page. Therefore, we can find the probability of this by a tree, which can get quite cumbersome, or we can use the formula as previously stated. Either way, we're going to end up with the same probability of 1/16. In this example, Raina has 2 red socks and 4 white socks in her sock drawer. Find the probability that she will randomly select 1 red sock and then, without replacing it, randomly selects another red sock. In this case, if A and B are dependent events, then we're going to use the probability of A and B equals probability of A times the probability of B, given that A has occurred. And this is dependent because she's not replacing that red sock. So we need to find the probability of randomly selecting the red sock originally. Therefore, we have to look at the total number of socks. And here we have 2 red, 4 white. We have a total of 6 socks. If she pulls 1 red, that's a probability of 2 out of 6. And we know that is simplified to 1/3. But now we want the probability of B is pulling the other red sock, but she already pulled one red sock. So now the total number of socks in a drawer has been reduced from 6 down to 5, and there's only one red sock left. Therefore, the probability of pulling the second red sock is 1/5. Now we just substituted in a formula for dependent events. We know the probability of A is 1/3 times the probability of B given A, which is 1/5. And our solution for the probability of the problem is 1/15. In this example, Beth has 2 red socks and 4 white socks in her sock drawer. Find the probability that she will randomly select one red sock, and then, with replacing it, randomly select another red sock. Therefore, this changes the problem from the previous problem to an independent events problem. And our formula will be probability of A, pulling a red sock, times the probability of B, again, pulling another red sock. The probability of A, we want to find the probability of pulling a red sock. The total number of socks in a drawer, 6. Red socks available, 2. Therefore, the probability is 1/3. Now we're going to replace that red sock, and we still, for the probability of B pulling a red sock, have 6 socks in the drawer, and since we replaced the red sock, there's still 2 available. And that, again, is going to give me a probability of 1/3. Now the probability of A and B is going to be 1/3 times 1/3, which equals 1/9, which is a significant difference from the dependent events problem. If A and B are mutually exclusive events, which means that A and B can't occur at the same time, then the probability of A or B equals the probability of A plus the probability of B. If A and B are not mutually exclusive events, they can occur at the same time, then the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Jason has 2 green, 4 blue, and 3 red shirts in a drawer. He chooses a shirt at random and does not want a red shirt. Find the probability that Jason will pick a green or a blue shirt. And here, if A and B are mutually exclusive events, then we're going to find the probability of A or B, which equals the probability of A plus the probability of B. The probability of A, and what we want is Jason picking a green shirt, is going to be the total number of shirts, 2. 4 makes 6. 3 is 9. Probability of choosing a green shirt is 2/9. And the probability of choosing blue is going to be 4/9. Therefore, the probability of choosing A or B, 2/9 plus 4/9 equals 6/9, or a probability of 2/3. Therefore, we also can determine that this is a mutually exclusive problem because I cannot select both a green and a blue shirt at the same time. Now in this problem, of the 20 members of the bicycle club, 7 were in race A, 8 were in race B, and 3 were in both races. Find the probability of selecting at random a club member who is in race A or in race B. A and B are not mutually exclusive because you could have been in both race A and B. Therefore, we need to determine probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. The probability of A is we have 7 out of the 20 group members were in race A. Probability of B is 8 out of the 20 group members were in race B. And 3 of the group members We're in both race A and B. Therefore, using the formula, we have 7/20 plus 8/20 minus 3/20, which equals 7 plus 8 is 15, minus 3 is 12/20, and we simplify that, and that's going to be 3/5. Which means if I change that to a decimal, that's 0.6 or 60%. A bag contains cards labeled with numbers. There are 3 5s, 1 4, 2 3s, and 2 2s. One card is randomly selected and replaced. Then another card is randomly selected. Find the probability. Since it's going to be replaced, we know that this is going to be an independent probability. Our first one is we want to find the probability of the first card is a 5 and the second card is a 3. Therefore, we need to find the probability of the first card being a 5. Let's see how many cards there are in total. 3, 1 4 gives me 4, 2 3s gives me 6, and 2 2s gives me 8 total cards. The probability of selecting a 5 is going to be 3/8. Since it's independent, I'm going to multiply that times this event, which is the second card is going to be a 3, since there's a total of 8. I know that this is going to be the probability of pulling a 3, 2/8. And when I simplify, 3/8 times 1/4, I get a value of 3/32. The next one, the probability of the first card is even and the second is odd. Again, it's independent. My even would be the probability of my 4 and 2s, and I have 3 out of 8 on those for even, probability of an even card, times the probability of an odd. I have 3 and 2, which is 5/8. Therefore, the probability is going to give me 15/64. A bag contains cards labeled with numbers. There are 3 5s, 1 4, 2 3s, and 2 2s. One card is randomly selected. Find the probability that the card is chosen to be a probability of a 4 or a 5. This is a mutually exclusive probability because I can't pick a 4 and a 5 at the same time. Therefore, I need to find the probability of a 4 plus the probability of a 5. And I'll find the sum of those probabilities. Altogether, I have 3, 1, 2, and 2 cards. That's a total of 8. The probability of selecting a 4 is 1 out of 8. The probability of selecting a 5 is 3 out of 8. Therefore, the solution is 4/8 or a half. Here, I want the probability of a 2 or a 3. Therefore, it's, again, mutually exclusive, so I need the probability of a 2 plus the probability of a 3. Again, I have a total of 8 cards. Probability of a 2 is 2/8. The probability of a 3 is 2/8. And their sum is 4/8. And again, I get a half.